Hello, welcome back. This is the mini lesson on action potentials. So we just got done covering graded potentials, which happens on the cell body and dendrites because of chemically gated channels. So now we're going to take a look at what happens when one of those graded potentials gets close enough to change the transmembrane potential of the initial segment of the axon, where our first voltage gated channels are located, which will then trigger an action potential, which will then be maintained and travel the entire length of the axon all the way down to the synaptic terminals. So again, here is our navigation picture. So we've already covered our transmembrane potentials. You can go back and review that if you're still a little bit unsure as to the sodium-potassium environment of the membrane. The last video was our graded potentials, which happens on the cell body and dendrites because of the chemically gated channels. We can either have depolarizing, where we get more positive, or we can have hyperpolarizing, where we get more negative. And then if that depolarizing potential is close enough or strong enough to the initial segment of the axon, it may produce, it may or may not, it may produce an action potential, which will then travel the entire length of the axon all the way down the telodendria to the synaptic knobs. Okay, so let's take a look at what's actually happening at that initial segment of the axon to trigger an action potential. Okay, so we're kind of in that middle spot with our navigator picture up there. So now we are dealing with these voltage gated channels. So you can go back and review those if you needed to, but for the sodium, so I'm going to try to draw them over here. So the sodium, I'm going to draw in purple. Okay, so there's the two gates. So at -70, we have the activation gate is closed. That's the one on the top. The inactivation gate is open, and that's the one on the bottom. And then we have our potassium gates at -70. It only has one gate, I should say, just one gate. And it is also closed at -70. Okay, so let's say we have a graded potential, and that's what this little red halo looking thing is happening. So again, it's on the cell body. We don't start the axon until the initial segment, but it's close enough. So imagine one of those graded potentials that we just saw is close enough and changes the initial segment of the threshold to -60 millivolts. What's going to happen? So let's see. We'll take it one piece at a time. So we're going to depolarize that initial segment to threshold. That's that -60 number because that's when the activation gate opens. So here's that local current, right? So that's our graded potential. So that influx of positive charges, influx of sodium coming in through the graded potential changes the environment right around that voltage gated channel. And at -60 millivolts, what's going to happen? Well, let's see. So over here, we are now going to be at -60. That is going to trigger the activation gate to open. Okay, so now that the activation gate is open, the membrane is permeable to sodium. So sodium rushes in. A whole bunch of positive charges are rushing in. So we know that sodium will continue to rush in all the way until it gets to +66. But if you remember in our conversation with voltage gated channels, that bottom gate, that inactivation gate, closes at +30. So if we continue to let sodium rush in until we reach a +30, okay, what's going to happen? Well, the inactivation gate closes, so no more sodium comes in. So we're done with sodium. But also, here's the magic number for the potassium gate. So at +30, the potassium gate opens. Okay, so in a simultaneous instant, the inactivation gate closes, so no more sodium can come in, but the potassium channel opens. So now potassium goes down its concentration gradient, which is out. Okay, so we're losing positive charges. Okay, at +30, the direction changes. So we've depolarized from -70, -60, opened the sodium channel, depolarized -50, 40, 30, 20, 10, 0, +10, +20, +30, and then at +30, sodium no longer can come in. So we stop the depolarization event, but now potassium is leaving because the potassium gate opens. So now we're losing positive charges, positive 30, positive 20, positive 10, 0, negative 10, negative 20. So we're kind of going on the downswing, repolarization. Okay, and this gate here, right around negative 60, right? So on our kind of repolarization down spin, right around negative 60, which was our threshold value, the inactivation gate of the sodium channel closes, opens, the activation gate closes, and they do it simultaneously, so no sodium's gonna leak, so it's kind of like open or closed, open, so it kind of goes, I don't know if you can see my hands, kind of like this. So inactivation gate is closed, activation gate is open, and at negative 60, they just change position. So the channel is still closed, it's just not inactivated anymore. And then the potassium channel starts to close at negative 60, but it does so slowly. And so as it's closing slowly, a little bit more potassium leaks out. And so we actually get a little bit of what we call a hyperpolarization. Ah, shoot, I forwarded my slide and I can't go backwards. So I'll just kind of recreate what was happening. So as this gate is slowly closing, we get a hyperpolarization and it goes all the way down to negative 90 millivolts. Okay, because potassium will continue to leak out until it reaches negative 90. And then by the time we reach negative 90, the gate is completely closed. No more potassium is leaking out. The sodium gate is back to its normal resting position with the activation gate closed, inactivation gate open. So we're now back at rest. And the reason why we get back to rest is because that sodium-potassium pump embedded along the entire length of the axon is continuing to pump. All the sodium that just rushed in is going to get pumped out. All the potassium that got rushed out is going to get pumped back in. So we're going to get back to rest. So this graph that I kind of forwarded to accidentally is more of a graphical representation of an action potential. I almost like it better than the picture of the gates, the gated channels, because it kind of gives you a lot of information. So let's do a highlight pen so we can kind of highlight over the steps. So we're going to start at negative 70. So again, negative 70, here's our gates over here on the right. The sodium channel is closed, the activation gate is closed, the potassium channel is closed. Here, between negative 70 and threshold, this step one, you have to have a graded potential somewhere near the initial segment. So it says graded potential brings an area of excitable membrane to threshold. Excitable means it has voltage gated channels. It can respond to changing transmembrane potentials. That's the whole point of voltage gated channels, is they're susceptible or sensitive to changing transmembrane potentials. So somewhere next to that initial segment, a graded potential happened. It brought that area to negative 60, right? So let's kind of see what's happening with our channels. Ooh, I'm still in highlighter. So negative 60 millivolts, negative 60 millivolts. What do the gates look like? Well, in the sodium gate, it becomes open. Potassium gate is still closed at negative 60. So with the sodium gate open, we get this rapid depolarization all the way from negative 60 to positive 30. So this is our depolarization stage. Okay, so then what happens at positive 30? So we got to remember positive 30. So what happens to our sodium gate at positive 30? Well, the inactivation gate closes. What happens to our potassium? Potassium gate opens. So that's the magic number to close or inactivate the sodium channel and to open the potassium channel. So then we get this rapid repolarization. And then right around negative 60, right? So potassium channels close and both sodium and potassium channels return to their normal states, kind of right around negative 60. right? So we're repolarizing back to -60. Well, I'm still in highlighter mode, that's right. Kind of shows up a little bit better. So then at -60, these guys go back to their close and close activation gate, open inactivation gate, and slowly closing our potassium gate. Because it's slow, we have this little undershoot of hyperpolarization right here, down to about -90. And then we are going to use our sodium potassium pump to get everything back up to rest, which is going to be our -70 millivolts. Okay. And then we're back to rest. This highlighter pen, it's hard to keep track of all the colors. There we go. Okay, so that's the action potential graphically, and then I kind of showed you what was happening with the channels simultaneously. The other thing that we need to talk about are these kind of boxes here, what's called the absolute refractory period and the relative refractory period. The absolute refractory period means an action potential is actively taking place. The sodium channels are open, right? So the voltage gated sodium channels are open. You can't open them anymore. They're already open. So even if another graded potential is hanging out right there as initial segment, there's nothing else that can be done because everything that's being done is already being done. So you basically, the refractory period is you cannot start another action potential during this time. In the absolute refractory period, absolutely cannot start another action potential. Once you reach the relative refractory period, we can trigger another action potential, but it usually has to be triggered with a higher than normal stimulus. So the difference between, here we go, the difference between rest and threshold is 10 millivolts, right? So in a resting cell, you start off as -70, you can trigger an action potential with a stimulus of 10 millivolts, going from -70 to -60. But what if you wanted to start an action potential down here at -90, when you're at the bottom of that hyperpolarization? You'd have to go from -90 all the way up to -60. That is a difference of 30 millivolts, which is bigger than 10. So in the relative refractory period, you can trigger another action potential, but you have to typically have a stronger than normal stimulus to do so, okay? So I know graded potentials, action potentials can be a little bit overwhelming and a little bit complex, so please make sure if you are struggling with these concepts, get help, come to office hour, Zoom office hour, send me emails, ask questions during lab time. Yeah. Okay, so that's the action potential mini lesson. I will see you next time. Bye.